Welcome back to some more geometry. Today we are looking at 3.2 statements, conditionals, and biconditionals. This is going to be a little bit long one. I didn't want to cut it into multiple parts, so I figure you guys can kind of skip ahead if you're good. I know in class we did take it over 2 days just because of so much. But let's start with just the simple basis. What's a statement? So a statement, again, just that. It's just a sentence somebody says. Is it true? Is it false? Who knows? But we do know that they are, I don't know why I cut off that P right there. Anyways, statements are represented by using the letter P or Q. Like we just use that to kind of like not having to write the whole statement out every single time. We just use, hey, statement P, statement Q. I don't know why they picked those letters particularly, the math gods, but that's the letters they picked. Now, truth value is just that. This is where we actually do a little bit of deep diving, like, is this true or is this false? So, for example, a rectangle, statement P is, a rectangle is a quadrilateral. And we figured out, that's a true statement, because to be a quadrilateral, you just need 4 sides. Well, rectangles have 4 sides, so that's a true statement, right? The opposite of that, or not the opposite, but the negation of that is when you make the opposite meaning of of any statement to cause an opposite true value. So we use this little squiggly P, the squiggly specifically. The squiggly means not. So when you see the original statement P, the negation is not P. Okay, so squiggly P, going back to our original statement, is a rectangle is not a quadrilateral. Again, the true value of that is false because we determined that it is a quadrilateral. So now the negation doesn't mean you're just putting the word not. The negation means you're doing the opposite meaning. So if the original statement already said, hey, a triangle does not have 3 angles, that was the original statement, the negation is this triangle does have 3 angles. So it changes that right there. All right. Now let's kind of go into a little bit more of what's going to happen today in the first part of the work. So compound statements, a little bit of English here, it's when you put together 2 or more statements, sentences, conjoined. Now they're conjoined in 2 different ways. They're conjoined by the word and, we call those conjunctions, and we are combining them by the word or, we call those disjunctions. But let's start with the conjunctions. A conjunction, again, compound statement that uses the word and. So for example, our P statement here is a rectangle is a quadrilateral, which is a true statement. And a Q statement is a rectangle is convex, which is, again, is also a true statement. So when we put it all together, we say a rectangle is a quadrilateral and a rectangle is convex, period. Now, is this a true statement? Yes or no? It is. It is. If you read below already, you know this is a true statement because both individual statements are true. And since both individual statements are true, then the whole statement is true. Now, you use this up arrow value right here. We use that to represent the word and. So when we combine our P statement and our Q statement, we say P, again, bell, P and Q. Okay, P and Q. So since both P and Q are true, then the conjunction. Now, at any point, if one of these 2 statements is false, then the whole thing is false. Again, with the conjunction, when you use the word and, the power of and, it says this first thing has to happen and the second thing has to happen. Okay, so at any point one of them is false, the whole thing is false, right? But with disjunction, it's a little bit different. Disjunction is an or value. It's a little more lenient. Say, hey, you could do this, you could do that, a little bit of this or that. So, for example, our P statement here is January is a fall month, which we figured out that's a false statement. Or January 1st is the first day of the new year, which that is a true statement. So when we put it together, we say, hey, January 1st is a fall month, or January 1st is the first day of the new year, period. This is false, this is true. But because one of these is true, the whole statement is true. So we talked about in class about how disjunctions are a way you can just answer a question. Again, as long as one of this is true, then no wrong. So let's say you ask your significant other, hey, do you want to go to Applebee's or do you want to go get tacos? And as long as the word that one of those you do want to do, you can say yes. I know it's kind of a smart butt answer, but yeah, it's not a wrong answer to say yes, I want to go to one of those 2. Now, if you want to be more specific, then you can be like, I want to go get tacos instead. But that is how disjunction works. As long as one of those is true, the whole statement is true. Now, this little upside down arrow or a V looking thing, that represents our or. That is or. So P or Q. That's how you'll read that. All right, so that kind of goes through that. So a couple examples that we did in the assignment. We say, hey, or in the practice, we said, determine if these are true or false. Let's look at this. We said P or R. So we start with this. This kind of give them already a true value. So the sky is blue. That's a true statement. The sky is purple. That's a false statement. Cows have four stomachs. That's a true statement right there. And they also talk about negation. So if the sky is blue, the negation of that means the sky is not blue. So that's a false statement. The negation of the sun is purple. So the sun is not purple. That's a true statement now. And the negation is the cows do not have four stomachs. That's a false statement. So we kind of keep these in mind. So when we look at this, say, all right, P and Q. So true statement, Q, R, true statement. So the whole thing is true. Not P, so the sky is not blue, or the sun is not purple. So the sky is not blue is false, but the sky is not purple is true. So the whole statement is true because it's an or. And then P or R. So the sky is blue and cows have four stomach. Individually they're true, so the whole thing is true. So that's how you'll see some of this assignment done. All right, so that's the first part of this. The second part of this is the conditional statements. With conditional statements, you're turning these statements into what we call an if-then form. So, but let's talk about the word conditional. Conditional, if you think about it in your kind of conditional love, I will only love you if you do this for me. So it means that something has to happen before the results can happen. So the if statements have to happen before the then statement can come to exist. So for example here, when we look at this, our P statement now is our hypothesis. So our if statement, if this happens, if the mouse steps on the trap, okay, that's our hypothesis, then the trap will spring. This is our conclusion. That's the conclusion that we create. So again, this is kind of like our conjecture. We're saying, hey, this is going to happen if the original thing happened. So for example, again, if a mouse steps on the trap, let's say the mouse did step on the trap, so that's a true value, then the trap will spring. The trap sprung. Okay. That's what we hope. That's what we hope. Now let's look at this truth value table. This table is the table of all possible combinations of true and false that can happen. Okay, and you look at this, there's only one false. So let's look at this, what this means. So let's say P is true, Q is true, then if P then Q, that's what this little arrow means. This is how you write this conditional. P implies Q is the what we call the representation, the symbol representation of a if-then statement. Just say P implies Q, and it's referring back to whatever we call P and Q. So for example, we're going to use this right here. P implies Q. So if the mouse did step on the trap, and the trap did spring, then the entire conditional statement is true, because the hypothesis happened, the conclusion happened, so the whole statement is true. But let's look at this one right here. What if the mouse did step on the spring, but the mouse did step on the trap, but the trap never sprung? Then our conditional statement is false, because the results never happened based off what we assume the hypothesis would have happened. So that's where the false comes from. The way I kind of explained this, let's look at this right here. I'm going to use this right here. Imagine this is a bomb right here, okay? And I lit the bomb on fire, so my core went off, my hypothesis went off, which was supposed to go ahead and make this, but it was just a dud. The Q never exploded, never expanded, never popped. It never exploded. So externally, we look at this like, wow, that's a dud. It didn't work. That's how that's what happens when your hypothesis is true, but your conclusion is false. The whole thing is false. But what about the other way around? Let's say the mouse never did step on the trap, but the trap still sprung. We're technically right as well, because we said this trap will spring. So think about it this way. Even though it might be a malfunction, let's say, hey, we never lit the bomb on fire. We never lit the fire, but it reacted and it caused an explosion. So did the bomb explode? Yes. So the whole statement's true, because the conclusion still happened. Another way we kind of talked about this in class is, let's say you have a partner, okay, and your partner is cheating on you, and you blame them. You say, hey, so we got partner A and partner B. You say, hey, you you're cheating on me. You are cheating on me, B, with a C over here. You're cheating with C. Well, come to find out, partner B is not cheating with C. No, that's not happening. Partner B, though, is cheating with E. It's happening. Cheated. But now, were you wrong to blame them for cheating? No. Did they cheat? Yes. The cheating still happened, but you just picked the wrong person who they cheated with. So, but were you wrong in accusing them of cheating? No, you weren't wrong. So it's still a true conditional statement. The action still happened, it's just with the wrong person. So that's another way to kind of look at false, true, implies true. Let's look at our last one here. So false, false, true. Like, oh, that's weird. Two falses isn't true. Sort of. So let's look at this right here. Let's say the mouse never stepped in the trap. So then the trap never sprung. Were we wrong here? No, because the action to spring the trap never happened. So we can't say the trap didn't work. Same thing with the bomb. If I never lit the bomb on fire and it never exploded, it doesn't mean I'm wrong because I never tested it. I never lit it on fire to cause the explosion to happen. So we can't say that is a wrong, a bad bomb. It just didn't work. All right, so that's conditional statements in a nutshell. Let's kind of look at other if-then statements so that you'll see. So if you live in Liberal, Kansas, then you live in Kansas. True. Okay. If you have feathers, then you're a bird. Again, if you have feathers, then you're a bird. It's a true statement. If we say how we see it in math, if 4x equals 20, then x equals 5. Again, this is how we usually see in math, but we usually don't necessarily look at them differently. We say, all right, 4x equals 20, so we conclude by dividing 4 on both sides that x equals 5. Well, that's an if-then statement. If this is the problem I gave you, this is the answer you gave me. So when we do math, we as teachers give you a bunch of if questions that I need you to make a conclusion for. You're giving me the conclusions, and that's what you turn in as your answers. All right, so let's look at a couple other ones right here. So if everybody at this party receives a gift, so how can we turn that into an if-then statement? Everybody at this party received a gift. Well, you can do it. Look at it in multiple ways, but one way you can say is if you go to the party, then what will happen, you think? Then you will receive a gift. Yeah, receive a gift. You can look at it just like that. Okay, let's look a bit more math to you. Okay, the area of a circle is pi r squared. Like, oh, okay, how do you turn that to if-then statement? The area of a circle is pi r squared. Well, we could say if it's a circle, then the area is pi r squared. Okay, and this is kind of what we do a lot with math. We say, hey, that is a triangle. So then, how do you find the area? You know, it's your base times side divided by 2. So this is where we say, all right, if you know what the shape is, then you should know the formula for that. And that's how we look at this particular problem right here. All right, so that right there is conditional statements. Now, part of conditional statements is sometimes we test these conditional statements in a different manner. So keep in mind, the conditional statement will always be the original statement that was given to you. We are not going to talk about 3 other things that we can apply to these conditional statements to determine the validity of these, if they're true or false or not. So let's start with the first one, converse. So remember, conditional statements come in the form P implies Q. Well, converse, what it does is it flips the two. Let's say, what if we say the conclusion comes first, and that's our new hypothesis, would that imply our original hypothesis that is now our new conclusion? So, for example, if it has feathers, that is our original P, then it's a bird, that is our new Q. So, with the converse, it'll go oppositely. We'll say, if it's a bird, this is our new P, then it has feathers. That's our new Q. There. Now, let's look at our other conditional statement. This kind of is more relatable, at least what we do in math. So if we look at this, our original statement, this was our Q, by the way. This is our P. Our original statement was if 4x equals 20. That's our original P statement. Then x equals 5. Right? Okay. With our converse, we flip it around. We'll say, hey, x equals 5. then is this true? 4x equal 20. And that is true. Now, because both statements is true, this is what we call a biconditional statement. And we'll speak on biconditional here in a bit, but this is what we call creates a biconditional statement. Let's look at other ways to check if our statements are correct. So with an inverse, we take our original conditional. Remember, conditionals come in the form P implies Q. We say, all right, let's go ahead and inverse this statement, or again, the inverse means to negate it, and determine if it's still a true statement, it's still a good statement or not. So when you negate the statement, you don't move the statements. You know, P still first, Q second, but you're going to change the value of that. So our original conditional statement that we were running with earlier was, if it has feathers, then it's a verb. Oh yeah, they're both true, okay? This is our original P, this is our original Q. When you negate that, you're saying, if it doesn't have feathers, then it's not a bird. Which again, that is also a true statement. So this is a valid statement, conditional statement that we made from the very beginning, because it still keeps the validity of that to be the same amount. They're both true still. So this is a good statement. Good statement. Good job, y'all. Way to create that statement. Let's look at our contrapositive here. Contrapositive kind of puts the two together. Remember, our conditional statement, again, I'm going to keep saying that 1,000 times. Our conditional statement comes in the form P implies Q. P implies Q. Now, contrapositive negates it as well as flips the statement. So it does the negation of a converse, or just negates it with a squiggle, and then converse it, flips it. So we're going to flip the two and then negate them both. So if it has feathers, that's our original P, then it's a bird, that's our original Q. Now that's going to come over here, and that's going to come over here, and we're going to negate it. If it's not a bird, so not Q, then it doesn't have feather, not P. Again, both true statements, so this is a good statement you guys made. Good job. And again, still keeps the validity the same, still true. So let's kind of look at this right here. So looking at both a conditional statement, a converse and the inverse, and a contrapositive, there's certain logistical equivalences that have to happen to determine if we did this right. So a conditional statement and a contrapositive will have the same logical equivalence to each other, meaning they will have the same true, they both will be true, or they both will be false. They'll have the same truth value. Same thing with the converse and inverse. They will either have the same truth or the same false. Let's take a problem that will have some false. So again, earlier we talked about if you live in liberal, then you live in Kansas. Live in Kansas. Okay, so that was our original statement. That was a true value. So you live here in liberal, you live in Kansas. Okay, what happens if we do a converse? Let's do the converse. Remember, a converse came in the form Q implies P. We flip it. So let's flip that our statement. So I'm going to shorthand a couple of these. So if you live in Kansas, then you live in liberal. Okay, liberal, LBK. So if you live in Kansas, you live in liberal. That is a false statement. Just because you live in Kansas doesn't mean you live in liberal. So the converse of that is false. What about the inverse? Remember, inverse keeps the statement the same, but it negates it. So not P implies not Q. What happens there? Well, let's look at that. If you don't live in liberal, so don't live in liberal. Let's skip it there. Then you don't live in Kansas. Is that a true statement or not? Don't live in Kansas. Yes or no? No, that's a false statement as well. Just because you don't live here in liberal doesn't mean you don't live in Kansas. So that's a false statement. So let's look at our contrapositive. Remember, our contrapositive, contra, comes in the form not Q implies not P. Luckily we did this already, so we can just flip those up top. We can say, hey, if you don't live in Kansas, then, almost like an arrow, I started doing an arrow, then you don't live in liberal. Assuming we're the only liberal Kansas, that is a true statement. If you don't live in Kansas, you for sure don't live in liberal. So that's a true statement. So let's look at this logical equivalences. Our conditional statement, our original one, has the same true value as our contrapositive down here. and then you look at our inverse and converse, they have the same truth value as well. So we created a logically equivalent statement that is correct in its statement and is setting itself right. So in the homework, when they give you the question, say, hey, here's the original conditional statement. I want you to write me the converse, the inverse, and the contrapositive. They can all be considered true. It is possible to be considered true. But if there's some that can be false, make sure that your original statement and your contrapositive have the same true value, because we did them right. And then the converse and inverse have the same true value. If they don't, somewhere along the lines, we messed up or we made the wrong conclusion. Now, our last thing, like I said, we're going to talk about our last statement right here, is our biconditional. Our biconditional statements happen when both the conditional statement and the contrapositive have the same truth value. When they're both true, we create a biconditional statement. Biconditional means two, so the condition forwards and backwards is both true. Okay, so it's true going P implies Q, and it's true going Q implies P. So because it goes forward to backwards, then it's a biconditional statement. So when you're asked to create a biconditional statement based off the conditional statement they give you and the converse, you say, all right, so the original statement says if points are collinear, then they all line on one line. Okay, that's true. We said, yeah, okay, the definition of, let's kind of actually draw this out so we can see what they're talking about. So here's a line, and here is some points right here on that line, because there's, again, lines are just a bunch of points all in the same order. So here's a bunch of points. So these points are what we call collinear because they exist on the same line. So they have to be all on one line. That's kind of the definition of collinear points, is they are only on one line. I can't draw another line and have all of those exact same points on there again. So we're good that way. Let's go the other way around. Hey, if the points lie all on one line, so all these points, that's our Q statement. If all these points are on that line, then they are collinear. Again, the definition of collinear is they lie on one line. So that's true. So our biconditional statement would say points are collinear if and only if. So this is what you're replacing the if and then with, is if and only if. So we still take our original P statement. Points are collinear if and only if they lie on one line. And that's how you'll write these biconditional statements. Hopefully that helps y'all, and I'll see you next time. Bye.